is finish up talking about the quantization of the electromagnetic field. And so again, this is just a, in some sense, physically something very simple. It's really, it's a theory of photons, but this really is what photons are. And but it's just photons don't actually interact with each other. They're kind of free. They're free particles by themselves. They do interact with charges, but we're not. What we're not trying to do is we're not trying to. So we've talked about free particle theories, which carry charges, like the charged Klein-Gordon theory, and we've talked about this free electromagnetic theory, the theory of the photon. And in principle, I've shown you how to write down the terms that couple them. But if you actually do that, then when you put these two theories together, you'll have terms in your Hamiltonian which are cubic in the fields, and you'll have a theory which no longer free theory, no longer exactly soluble. You can't just write everything in terms of nice formulas involving quadratic operators. So that's what we're not going to do. Yeah. So this is what you have to, again, what you're going to have to do. What you have to go and take a real course in quantum field theory to do is to understand how interactions work. That's just a much more complicated subject. But I am going to do something with the electromagnetic field. It's the free electromagnetic field, but there's something really quite intricate about it, which is how gauge symmetry works. And this is something which was historically, it took people quite a while to figure out, and it's still a fairly confusing business. So I want to, in the context of the simple theory of the photon, kind of try to explain the various intricacies of how gauge freedom works. And if you take a more advanced course, a course in Yang-Mills theory, where when you have interactions, then you have these problems in an even more kind of complicated form to deal with. But at least we'll show you what happens from Maxwell's equations. Okay, so let me start by I'm going to start by finishing up what I did last time, which was the Coulomb gauge. Let's see where. Okay, and so what this is So this is an example of what's sometimes called a physical gauge. The point is that what you do. Well, remember, first of all, we had the condition A0 is equal to 0. So the first thing we did was choose a gauge transformation so that we got rid of the time-like component of 0. But then we had the problem with the theory is that there's still so the space of solutions is still invariant under time-independent gauge transformations, and there's an infinite group of these time-independent gauge transformations. You have to get rid of the effect of that somehow. And what actually works for in the case of electromagnetism for the U1 theory is you impose a condition that the spatial part. The spatial part of the vector potential is equal to 0. And sometimes you say that this is, or in momentum space, says that P vector so that the components of A are transverse to the direction of the momentum. Look at it in momentum space. Okay, and yes, and so this is what's anyway. Yeah, this is the condition that's called Coulomb gauge. And then let me see how far I got. I'm not quite sure how far I got on that last time. But then, okay, then what you show is that Maxwell's equations. Okay, so this is a Hamiltonian system. And what it is really so you have coordinates m. They're just the vector potential at a given time, and then the course. So these are kind of like your Q's, your configuration space coordinates, and then you have the analog of the P's, which are things that are you have to put in a minus the electric field. So it's pairs of these, and the idea is that this is data. I mean, this is always true, and this is data that at time 0 is supposed to specify a unique solution to the Maxwell's equations. But in order to make this unique, you have to kind of you have to add an extra condition, which is this one. So it's this space plus the condition. And this is what's called a okay. And then what happens is that then ddt of, anyway, if you set this to equal to 0, then ddt of it is going to be the Gauss's law. Anyway, let's say, and then what you get here is what's called a physical gauge, that if you take your phase space to be this data, the subspace of this data satisfying this condition, then you're going to then you've got kind of you've totally got rid of gauge freedom. All degrees of freedom are kind of physical degrees of freedom. Okay, and then in this, then the equation of motion. So in these coordinates, the equation of motion is going to just be the wave equation. So it's a so you can think of this. This is data which specifies a solution to the solution of the wave equation. Or you can think of it, the Hamiltonian generates time translations generate a path in this space, and if you think of that path as your a vector of t and x, then it satisfies the wave equation. Okay, and so then what you do is you then just you quantize this as basically just the 3 copies of the Klein-Gordon equation. This is just really you just have kind of an extra index on A. Otherwise, this is just exactly the Klein-Gordon equation. And what you do is you okay. So you have so solutions. You can write them, and again, okay, it's RA. Let me not start writing. Anyway, let me not write out all these Fourier expansions of these things. These are, you can look at these things in the notes, and this is not so interesting. But let me just kind of say what the anyway. You just write out exactly the same thing you wrote out for the Klein-Gordon equation, but with an index that goes from 1 to 3, and then quantize it in exactly the same way with Navier creation operators. But you have an extra. So this is 3 copies of AG, but plus a condition. So the problem is this condition, or if you like, this condition, and this condition is that p vector. So condition on. So you have these alpha j of p vector. These were the Fourier coefficients of a solution, and the condition is just that p vector dotted with alpha. And now I'll put a vector index, means I'm looking at all 3 of these guys. The vector is equal to 0. Okay. So you've got 3 for each p vector, you basically got kind of these three coefficients, and these guys are going to turn into annihilation and creation operators. And but you don't actually really have three of them. You actually only really have two of them are physical, because there's one. You've got these three coefficients and kind of three sets of operators, but you've got kind of one condition on these three operators, which is this guy. Okay, so you have to kind of deal at the so you have so you want to, in some sense, you want to write an expansion of solutions explicitly. So you want to kind of write out. You don't anyway. You can write this thing out, which looks like three copies of the standard expansion, and then say, but you're also going to satisfy a condition. But instead, what you'd like to do is, you really don't want something that's got all three of these guys in here. You want to, in some sense, solve this constraint and write everything in terms of the two real degrees, the two actual degrees of freedom. Okay, so here's the standard. I'm just going to tell you the standard story about how you do this. Okay. To solve vector anyway, p vector equal to 0 and get two actual degrees of freedom. Well, the standard thing to do is to introduce a basis of solutions. So you've got anyway. So you want to. So you introduce a basis of solutions to this, and you call these things and for each p there's going to be two solutions, and so you call this epsilon 1 of p vector, epsilon 2 of p vector. Okay. So for each p vector, so to kind of see what you're doing here, imagine, think about a sphere, and what you've got is some particular p vector, and what you want to do is you want to find a basis of the space which is orthogonal to this, which you can think of as the tangent space to the sphere at this point. And so what you want to do is you want to find at each p, you want to pick an epsilon 1 and an epsilon 2, and anyway, so there's a two-dimensional space of these guys. So for each p, you want an epsilon 1 of p and an epsilon 2 of p. So what you want to do is you just want to find a formula for, depending upon p, for two linearly independent or better or two orthogonal vectors, which span the tangent space to the sphere at each point. Okay. Now there's a little bit of a problem here. So anyway, you can find explicit formulas for this thing as a function of the of where you are in the sphere, as a function of the coordinates of the sphere, or the two angles that describe the sphere. But note, there's a subtlety. Which is that you can't. There does not exist just a continuous non-zero vector field on the sphere. In other words, if you, I mean, you can do this at any point, but if you try and make this choice, if you try and figure out, okay, I'm going to pick epsilon 1 here, and then I'm going to make a continuous choice of such a thing everywhere. That what you find is that there's a you run into a theorem in topology which says that you can't comb the hair in a sphere. Okay, so you can kind of see there's kind of a topological reason why you can't do that. You can't do this continuously. If any way you try and do it, you're going to find that there's going to be some point where you have to have a zero. You have to have a zero, and then you're not going to be able to give that unit length. Okay, so there's this topological problem. Now the general I think the general wisdom is that, well, that doesn't really matter, because the fact that there isn't really a good choice of this doesn't matter so much, because the things that you're gonna actually calculate in the end are going to be independent of this choice of this. So if you're running into some problem that at some point you don't have a continuous choice of this, well, you can always move that problem around anywhere you want and get rid of it and get it out of the way. So that's the general. And as far as I know, this is actually true, but I've never actually completely convinced myself that this doesn't actually give you a problem. But anyway, so anyway, so we're going to assume that we've got these guys, and that these satisfy p vector epsilon j vector epsilon. Yes, so remember that so these guys, this is an index which just labels the first one and the second one, and each of these guys is a vector. So p vector dot epsilon vector, then j of p vector is 0. So these things are orthogonal to p vector, and then what you also want to make them, and you want to make them orthonormal. So epsilon 1 vector dot epsilon 2 vector here is always equal to 0, and epsilon 1 vector squared. Okay. And so these things are called, to give it a name, they're called polarization vectors. So if you look at any of the formulas people are going to use to actually do calculations of this theory, they've at some point introduced, they've made some kind of choice of these polarization vectors, or more likely they've just kind of written everything in terms of these vectors, saying, we've picked some kind of vectors which satisfy this, and anyway, and then you just work in terms of these things, and then you end up with formulas that, in the end, well, anyway, in the end, typically you're looking for physical quantities that are kind of independent of how you actually chose these polarization vectors.
Good question.
Yeah.
Why are we looking at S2 for a U1 theory?
Well, it's just the.
Or are we? Oh, I guess we're restricting to.
Well, you're just looking for solutions as a function of p of this guy. Yeah. So for and I guess, yeah, that one thing that so for a fixed if you can solve this problem for a fixed p vector, then yes. So these then. Anyway, you're looking for a solution that doesn't really depend upon. Well, anyway, the solution.
So the magnitude of p is not really going to matter.
Not really matter.
We just want to look at the tangent space of S2 because we can get a general picture there.
Yeah, exactly.
Okay,
that's all.
Got it. Thank you.
And then maybe another relevant thing to say is that you also can worry about that something funny is happening at p vector is equal to 0. Yeah. So one thing about these techniques also is that there's one. You're finding kind of oscillators for every possible value of p, but what's happening at p equal to 0 is yeah, I mean that's clear. It's clearly I mean, your methods are not kind of dealing with this one case. But you know, you've got this infinite dimensional thing you're dealing with. There's a one kind of, you know, there's this finite dimensional subspace at p equals 0, and so actually I think there maybe are some interesting things to say about this if you actually look at this. Yeah, so something interesting is happening at p vector is equal to 0, which I'm not talking about. And p vector is equal to 0, remember, is the kind of the constant. So as you're approaching p vector is equal to 0, you're approaching very, very large distances. So in some sense, what's happening here, how you specify that kind of corresponds to what are you going to do about boundary conditions as you go off to an infinity. Okay, and then there's a lot of interesting, and anyway, there's kind of interesting symmetries of this whole situation, you know, that kind of act on the boundary conditions at spatial infinity. There's a whole interesting story about that, which I'm not getting into, but it's because I'm really I'm telling you, don't look at what's happening here.
Got it.
Okay.
All right.
Okay. Anyway, so then what happens is you then write in anyway, so then you write down an arbitrary solution. You expand it in terms of instead of using these coefficients, you expand it in terms of these guys, and then instead of having kind of 3 coefficients, there's going to be 2. There's going to be the coefficient of this guy and the coefficient of this guy. And then if you write down finally the equation for your field, what your field does, it's the x vector. It's here. This is a standard normalization. Here you've got one. It's basically a sum of oscillators, one for each p vector. But now you're going to have so you're going to sum over these two coefficients of these 2 polarization vectors. So I'm going to call, and so I'm using a term sigma. You're going to sum over sigma is equal to 1 and 2, and then what you've got for each term of the sum, you've got an epsilon sigma of p vector. That's this guy. That tells you what that picks out a direction in 3 space corresponding to this either 1 or 2, and then you've got your usual. And let's see, I got it p vector. So then you got your alpha bars, which have turned into annihilation operators, and then e to the minus I omega p vector t e to the I p vector dot x vector. See if I got it. And then you got the creation operators that are also the corresponding to these guys. And then just the adjoint of this, so e to the omega p t. Okay, oh, that's right. But so it's really just the same thing. So instead of having a sum, what you originally had, which was a sum of 3 copies of the actually, sorry, I guess I should. Yeah, so what's true is that this actually then has a vector index, and then remember that these guys you have to remember are vectors. That's the point. Okay, so I've just done something a little bit funny in order to solve this constraint. I've instead of writing a sum over three of these guys, I've written a sum over two of these guys are the things that solve the constraint. Okay, and associated as coefficients of these guys. Now, instead of having three sets of annihilation equation operators, of course, which would be if I just had 3 copies of Klein-Gordon. Now I've got two copies of them, and these just satisfy the usual conditions. So that this is your field, and then he's really just a bunch of oscillators, which is standard kind of oscillator things with and you have a sigma of p vector, a sigma prime of p vector prime dagger. So the A's and A's commute, and the A's and daggers commute. The thing which doesn't commute is this guy, where you have when sigma is equal to sigma prime, you have a delta vector. Okay. And so there's a standard kind of distributional story about these operators, but it's basically just it's a standard story of just a collection of annihilation and creation operators for quanta of harmonic oscillator quanta, one for each p, and there's 2 of them. So.
Well, I have a question here. So the A delta or A star delta, so do they serve something like a cotangent vector, so that they can pair with the epsilon delta and the E delta?
Well, I mean, so what's true here is
So how do you make it a good definition?
Definition of what? Of what?
The epsilon delta is not globally defined. So do you do something in A delta so that you can make the integration globally defined? So is A delta a kind of something cotangent vector? Something.
Well, this problem I was telling you about these guys. I mean, this is the only thing that you have to worry about is that there may be points. Yeah, anyway, is that these things have a actually you if you look, you can find perfectly decent formulas for these guys, but then if you look at these formulas, you'll find that they have kind of a coordinate singularity at certain points. Okay.
Yeah, so that's what so can I say like A delta serves like cotangent, so that A delta is a cotangent and epsilon delta is a tangent. So when they come together, they become every way defined thing.
Yeah, I don't actually. Honestly, I'm not sure. It may be. Yeah. It's possible you can think. It's possible that you can think of the definitional problem that there's going to be a point where there's a problem in the definition of these with. You can have some corresponding problem here so that the combination doesn't have a problem. It's possible. I haven't really thought about it. You know, but the yeah, but in some sense this is going to be an infinite sum of these oscillators, and there's just going to be some there's going to be some, depending upon how you define these guys. There's going to be one point where something funny is happening. There's going to be one particular value of p which is funny. If you try and there's one place where you couldn't copy, or well, there's actually have to be 2 for topological reasons. There's 2 places you couldn't that where this definition is not right, but it's out of an infinite collection of oscillators, there's just going to be 2 of them where you have the problem, and the problem can always be moved. But I'm not sure. Yeah. Anyway, I'm not sure. I think I know what you're asking, and I'm not sure. It may be that you can think of this combination as not having that problem. I'm not sure. Okay. Yeah.
I guess like does the integral like behave strangely around that point, or can you just? I mean, it's a measure 0 point. Can you just? Yeah. So I don't know.
Yeah, I mean, I think that's the general argument is that these are all kind of distributional equations, and there's some kind of problem at points, but you don't care about what if some problem at point at measure zero. That if you integrate this against any kind of well-behaved function, you're not actually going to see that problem. Yeah. Anyway, I believe anyway. I've never actually sat down and worked out. I believe there are many ways of. It's interesting to see if this problem occurs, but I can see many ways you could argue your way out why it's not going to matter. But I haven't actually checked them to see to make sure that which ones work. Okay, but that's the anyway. But this is the general idea. And let me see. So what you've got. Okay, so maybe before. So let me just. Anyway, so this gives you. I mean, this thing is just an infinite collection of oscillators with labeled by p vector and by sigmas equal one or two. It might be interesting to just to go back and say what if you're going back to x space. So Fourier transform going back x vector space, and thinking not in terms of these operators, but in terms of these a of x vector. So what you have is that you have these the use of those polarization vectors and these commutation relations correspond to these. So a k x vector prime. So these are like your Q operators that they commute, and same thing with the P-like operators, which would be E at J of X vector. Okay, so but the interesting commutation relations are supposed to come from the thing is that the analogs of a Q and the analog of a P, and so you get something on zero if you try and compute this guy. Okay. Okay. So it turns out what you get is, well, there's a what you get is well, there's a minus I. There should be a minus sign here, and then there's a standard I from Q commutated with P gives you an I, and then you have a 1 over 2 pi. So normally you would expect to see a delta of x minus x prime over here, but what you actually see is if you compute as you see is something different because of the fact that you're not just doing three independent oscillators is that what so you have an integral, and then there's an e to the I p vector dot x vector minus x vector prime p cubed. Okay, and this is what you would expect the delta for the delta function. And then also a delta and a delta JK. But what you actually end up with is a term here, which is delta JK minus PJ PK over P vector squared. So what you actually have, so you have kind of a weird. You don't quite have a delta function that you expect. You have kind of a delta function which has built into it kind of a projection onto the transverse degrees of freedom. So this is kind of a delta on the transverse degrees of freedom. Okay. So something anyway. If you're actually trying to do calculations of the subject, you run into the fact that things behave nicely if you work if you use the polarization vector trick to work with these particular things, which is a nice diagonal, well-behaved thing in momentum space, but if you try and work in position space, you end up with this kind of thing to struggle with. Okay. So then let me just say a bit about then kind of symmetry. How this theory then behaves under space-time symmetries. And so one thing you can ask about is time translations. And this is just a question of what happens to the Hamiltonian. So the generator of time translations is the Hamiltonian, and the Hamiltonian, if you compute it, I won't. Hamiltonian operator, what it is it's a half. Okay, you can write it in position in the position space with respect to these guys, or you can write it with respect to these guys. And let me just say, anyway, you can play around with these formulas, but it's similar to it's very similar to what happens in the Klein-Gordon case. What you have is you actually have the easiest thing to understand is what happens in momentum space. And then you just have a standard energy of the oscillator of momentum p times a1 times the thing which counts polarization, the things and then the thing which counts polarization 2 things. Okay. So it's just the kind of thing you expect. It really is exactly 2 copies of the. You really just have 2 kind of independent oscillators. The one that's in the epsilon 1 direction, the one that's in the epsilon 2 direction, and you're just counting the number of photons with each of those each of those polarization directions, and multiplying by the energy of a photon in momentum p. Or if you like, you can Fourier transform. You can write it in terms of these operators, and then you get this kind of the standard thing that you get by kind of that corresponds to kind of quantization of the classical energy function, which is, so you get a half, and then you have an E, the E operator squared, the sum of the squares of this guy, and then you have to take the B. So it's going to be a half E squared plus B squared, and B squared is the same thing as so remember, B is the curl of A. So you compute this guy. Compute this guy and take the sum of the squares of the components of this guy, and so this is your B vector squared, and it's just this guy. And then you just have to be, as always, you have to be a bit careful if you're working with these guys, these X vector things. You have to normal order for this to give you a sensible computation for this to be 0 on the vacuum states, and anyway, be X vector. So it's a little bit similar to the anyway. So you had something very similar for the Klein-Gordon case. The Klein-Gordon case, you just had had one oscillator like this, and you had instead of having these 3 components and just having the transverse and only the transverse thing contributing to the energy, you had a d phi dt squared and a grad phi squared terms in the standard Klein-Gordon story. So it's just similar to that, except you're only holding at kind of transverse degrees of freedom because of this. Okay, maybe just one last thing is to say about you can do the same thing with spatial translations, and you can compute what happens. I mean, this theory has a symmetry under spatial translation. What's the generator of that symmetry? That's the momentum. You quantize it, it's momentum operator, and again you have a so for spatial translations. The thing which generates spatial translations is the operator P vector. Oh, well, it's called vector hat, and this thing is going to be it's just the same as this guy. It's R cubed. Now you're going to again take the sum of these guys. And the only difference now is you have to be multiplied by the momentum. Instead of, so you have it has three components, and of course just the component momentum. So it's just counting the component of the momentum in each of these states. Okay, and if you again if you Fourier transform this and see what happens if you work in with A's and E's, you get P vector. You get that this is R cubed. What is it? It's just it's E vector cross E. And so and by this I mean del cross A. Well, del cross A vector if you like, and again you have to normal order it. But this again, this corresponds to something. If you take an E&M course and you kind of ask what's the what's the momentum carried by an E&M field, you've at some point you run into this formula that the right answer to the right answer to what's the energy in an E&M field, it's Z squared plus B squared is the energy density. What's the momentum density? Well, it's E cross B. Okay, and then the one thing that I think I decided not to work out here is you can also work out what happens to for rotations. So for rotations, what's the the generator of the angular momentum is the generator of rotations. The operator is going to be the angular momentum operator. So you're going to have a J vector and an operator, and it's going to have two kinds of pieces. It's going to have a standard L plus kind of a spin piece, but this is significantly more complicated than what happens in the anyway. I think I gave at least in the book I gave a reference where somebody had worked out this, but the calculations get trickier than even in the spin 1/2 case. But it's a similar story. You can write down formulas again in terms of the A1, A2 analytic creation operators, or in terms of the E vector and B vector combinations of A. Okay. But I won't get into that. And maybe the one other thing to note is that the for each P vector, so you have these epsilon 1 and epsilon. You have these you have these A1 and A2. You have an SO. You have an SO2 rotating, acting on the you can mix. Anyway, there's a the Hamiltonian is symmetric under kind of taking a cosine, multiplying this two-dimensional vector by some SO2 matrix like cosine theta, sine theta, minus sine theta, cosine theta, and so you can kind of do rotations in this space, and this corresponds to this phenomena that we had when we kind of tried to analyze, what are the irreducible representations of the Poincare group going to look like? Well, if you picked for a fixed value of p, you ask what's the subgroup of the Lorentz group that's going to stabilize that and leave that alone. It's going to be rotations about p. There's going to be, so this is this corresponds to rotations to the stabilizer group of p. So rotations about p, and then to the helicity. And so you can, anyway. So what you want to do is, if you want to, you can then diagonalize this SO2 action on these guys and look for look for things that are kind of complex combinations of this that have kind of charge +1 under this guy or charge -1 under this guy, and that's the to helicity. So you get states with helicity ±1. Okay, so if you take complex linear combinations of these guys and use diagonalize this SO2 action, you're going to have things where there's X with kind of SO2 helicity charge 1 or helicity charge -1, and that's going to, and this is going to correspond to what are called to photons that are left circularly polarized or right circularly polarized.
So is this kind of SO2 rotation corresponding to the SO2 rotation of epsilon 1 and epsilon 2?
Sorry, I didn't understand.
I mean, you draw epsilon 1, epsilon 2 as an orthonormal base at p. So is it corresponding to that kind of rotation?
Well, I think that if you're trying to think about photons, so if you're trying to think about how to think about photons states, you can. The point is, if you have for each choice of p vector, there's going to be so for each choice of p vector, you're going to have this kind of transverse space in which you can have epsilon 1 and epsilon 2. And so you can think about, if you want to think about, what are photon states with momentum p? Well, you can think of them that you can say, well, there's two kinds. There's a two-dimensional space in which they live, and you can have some which correspond to. You can think of them as oscillating in this direction, and you can think of some of them as oscillating in this direction. So that's one basis for your photon states of momentum p. Okay, but the point is, and that's in some sense the basis corresponding to these A1 of p's and A2 of p's. But the point is that you can actually, since these states, it's a complex vector space of states. What you can also do is you can also, and so these are just the two kinds of transverse oscillations, and you had to kind of make some choice of polarization vectors to decide which is 1 and which is 2. But that's just a basis. But you can also consider something. You can also ask, well, what about A1 of p vector plus or minus I A2 of p vector? Okay. So in other words, you can since these states are complex, you can complexify these operators and then and look at these complex linear combinations of these guys, and then these guys are the things that, so under SO2, these things just rotate into each other. Under SO2, you know, these things, anyways, so these things stay the same under SO2. The plus one just goes to e to the I theta of itself, and the minus one just goes to e to the minus I theta of itself. So this when you can complexify and diagonalize the action of that SO2, think of it as a U1 and diagonalize it. It's really, again, it's exactly the same thing we did very, very early in this class when I asked, you know, you know that SO2 acts on R2. Well, we're interested in complex unitary representations. You know, if you complexify, what do you get? Well, you get plus one and minus one charge things, and that's these guys. And so this physically corresponds to thinking about, you know, these guys correspond to a basis where you think about your photons as being kind of moving as being have transverse oscillations in the transverse direction to the p vector. These guys correspond to what you think of physically as kind of right and left circular, things that are polarized in the direction of motion, either with, in this quantized way, either with plus helicity or minus helicity. But you can you can go back and these are just two different bases for the complex space of states of photons with momentum p, and you can either think of use this transverse basis or use this circularly polarized basis. Okay, is that clear enough? Anyway, but but a lot of this is kind of very real physics about what you if you're doing something with photons, you want to prepare them typically in some state in which they're in one of these polarizations. They're polarized in some direction, or they're circularly polarized in one way or the other. So typically, you want to prepare your states of photons to be and to be kind of doing something very simple in terms of one or other of these bases. Okay. Okay, so that's, now let's see. Okay, so now, anyway, so this is all, I think, should be in pretty, you can find a more detailed version of this in pretty much any standard quantum field theory textbook, especially the older ones. But let me kind of just tell you some more. Let me tell you some more tricky things about quantization. So, not sure how much I'll have time for, but. Okay, so let me just say trickier aspect of well, let me just say this tricky. So let me just say this. So there's other ways to deal with gauge symmetry. Okay, and so there's kind of one problem. I mean, there's something that's not completely satisfactory about the Coulomb gauge. So one problem with the Coulomb gauge is it's not Lorentz invariant. And so if you actually try and do calculations in Coulomb gauge, as long as you have this nice theory of non-interacting photons, nothing too bad happens. It's pretty easy to see what's going to happen. The minute you actually try and have an interacting theory, life starts to get pretty miserable, because you've got problems with renormalization you have to deal with, and if your calculational method is not Lorentz invariant, ugly things get really ugly. So that's the general problem. what you find in and let me maybe start with this. So, well, actually, maybe before I get into this, let me first tell you another thing. So an alternate. Root. Well, an alternate method, let's say. So first, I'm going to tell you about just try to say this very quickly, because this is not something that you actually typically try and do, but it's something that you can in principle do, and people have their reasons to think about it is to so recall the problem was if you just did this, if you just went to time-like gauge and didn't impose the Coulomb gauge condition, is that you don't have gauge, no Coulomb. You don't have Gauss's law. So what you would like is Maxwell's equations to be to be operator equations, and your operators satisfy Maxwell's equations, and great. But the problem is that you don't if you work in time-like gauge, this is just, and you do a quantization only imposing this condition. This is basically just not true. This is not true. So you don't have this. And one way to think about it is that so you might want to think about what you've got is you're in some sense allowing all states. You've got a theory in which this is not true. So that this could be something. And if you go back to electromagnetism, remember saying that del dot E is something. Gauss's law says that if you've got some kind of charge at X, this del dot E is that charge density at X is what you expect. So in some sense, what you've done, if you just try and quantize your theory in time-like gauge and don't impose the Coulomb condition, is that you have a theory which is way too big. This is not true. That it includes states where del dot E is kind of any function you can imagine. So it includes kind of charge densities everywhere, which are not what you want to be dealing with. So what you can do, so plan is to impose the condition. So this is not true as an operator, but impose a restriction on states and say that psi is an element of a we've quantized in too big a Hilbert space, and you want some subspace of physical states which satisfy if L vector dot E vector psi is equal to 0. Okay. So the idea here is that you can what we're doing here is that anyway. So we're kind of this is something where I think I better stop and not try and. There's a lot more details in the notes, but you want to think of so classically L vector dot E vector is the moment map for time-independent gauge transformations. Okay. And so what so the source of our problem in the whole source of our problem in the time-like gauge is that we still have this extra symmetry of the theory, extra infinite dimensional group acting on the theory, which is the group of gauge transformations that are time independent, that don't change in time, and we have to somehow get rid of those. And you can ask, what's this group acts on this infinite dimensional face on your phase space of your A's and your E's, and what is this moment map? Well, its moment map is this function on the phase space. And so there's kind of a general principle that it's kind of like, if you want to get rid of that, if you want to look at things what we really want is we want things that are invariant under that. So one thing we could do is kind of fix the value of this to be 0 and then divide out by the gauge symmetry on the phase space. But the other thing we can do is this. And what you should think of this statement as being is, this is the statement that corresponds to saying that, so this corresponds to saying that a psi invariant under time independent gauge transfer. Okay. So the other thing, there, whenever you kind of quantize, there are two things you can do. You can impose the condition, the invariance of the group condition as a condition on the phase space and make your phase space smaller and then quantize. Or you can quantize the bigger phase space and then impose the condition on the states to say that, okay, well, what we've done is we've now created we've created a quantum theory where the states are transform under this group, and we actually only care about the piece of the theory which is invariant of the group, and that's what the Gauss's law is telling us. And so you impose this condition here. Okay. So here, I'm sorry. This is just kind of philosophy, but it's a philosophy which also extends to the non-abelian case. In the non-abelian case, you also have a Gauss's law. You also have the same problem. You can go to you can easily go to time-like gauge. You still have the problem that you have time-independent gauge transformations to worry about. You still have a Gauss's law, but in the non-abelian case, what happens is that this derivative just becomes a covariant derivative, and so then the problem is that this condition is no longer linear in A, and so all sorts of other hell breaks loose. So, but as a matter of principle, that may be, and that's supposed to be in some sense answer the question of how to get rid of the gauge symmetry. It's not actually it's not actually a very practical way of working here, and it also runs into even more problems of principle in the non-abelian case. But in principle, that's one way to think about what you're trying to do. And it's just a general thing about gauge symmetries. You can do you mod out in the appropriate sense the gauge action on the phase space and work with a physical phase space and quantize it, or do you quantize the whole phase space and then pick out a physical subspace by a condition like this? Okay, now more interesting, but it's going to have some other interesting problems, is to try to use this idea to get a Lorentz invariant way of dealing with gauge symmetry, and this is what's called a covariant gauge. So let me tell you about this and about some of the thing, what happens if you try and do this. And this corresponds to something which you'll see. Again, now we're getting closer to what's a typical story that's actually in the standard quantum field theory textbooks, because there, if you want to actually do calculations, you want to work with a covariant gauge. So let's see. So covariant. So here. gauge. And what this means is that if you the Lorentz transformations preserve the gauge condition. That's what I mean when I say it's a covariant gauge. I mean, so we want to pick a gauge condition such that if we know it's true, we do we do a Lorentz transformation on the whole story, it's still true. And so the standard, the simplest one of these guys is Lorentz gauge. And to make this really confusing, this Mr. Lorentz was not the same guy as Mr. Lorentz. So there's no, watch out, no T. So Mr. Lorentz was a different guy than Mr. Lorentz. But his gauge, which you call that, is you say that the, you take the combination of coefficient of coefficients of the gauge potential, which is given by this. You take minus d a0 dt and add and sometimes in the standard notation with upper and lower indices, that you'll find that this is often written d mu a mu. And so anyway, but this is anyway. This guy is explicitly Lorentz variant. If you Lorentz transform this guy, he'll still be zero. Okay, now what you can do. Okay, so what you want to do is you then show, and this is a not too illuminating calculation, but again that I did in the notes. What you show is, and you show Maxwell's equations plus this condition, plus Lorentz gauge imply that you get let's just say d squared. Let me write it this way. What am I doing? Sorry. No, it's wrong. It's minus. Okay. Now what have I done here? Okay. Oh yeah. So sorry. And okay. Sorry. So what happens is you get this, and also Okay, so what we're doing here is we're not so this is not time-like gauge. So the problem with time-like gauge is that time-like gauge really wrecks Lorentz invariance, and then the Coulomb gauge kind of further wrecks it. So what you want to do is you want to include both the spatial components and the time components and show that they just satisfy the standard wave equation. Okay, so the and that's true. That this is true. These things satisfy the standard wave equation. If you assume that Maxwell's equations are true, and that the Lorentz gauge condition is true. Okay. So okay. So then what you want to do is then the idea. Let me just tell you what the idea. So the idea is just quantize. And I guess now I'll just use a four-dimensional index, a mu, use as 4 copies of kg as 4 kinds of oscillators, and so mu is equal to 0, 1, 2, 3. But there's a problem that when you do this, but in order to do this in a Lorentz invariant way, maybe I'll say it this way. So then, or in other words, you write solutions as a mu of, you write solutions of this guy as a mu of t x vector is again 1 over 2 pi he has r cubed, and then you just put in oscillators, one for each value of mu. Anyway, the usual thing. P vector, not x vector. P vector. But now in order to get a kind of Lorentz invariant. So then the conditions that these guys are going to satisfy, so they're going to so these guys are going to solve solve the wave equation, but they've also got plus okay, and then and with a mu of p vector, a nu of p vector prime is equal to delta mu nu delta cubed of p vector minus p vector prime. But then the problem is you have to put it in order to make this whole thing be Lorentz invariant. You have to treat the time guy as for this to be a Lorentz invariant formula. You have to treat so plus for u is equal to 1, 2, 3, and minus for u is equal to 0.
You just put the Minkowski metric in there instead?
Yeah. So these guys are basically a basis. You're just writing out. So you're writing out kind of. So you have this nice Lorentz invariant wave equation. Okay, and you're just writing out solutions to it. It was in a Lorentz, and you need the coefficients to be Lorentz invariant. And in order to, anyway, and you basically have one way of saying it is that. Oh, sorry, this guy has a. Where's his? He's got this guy. Yeah. So, I mean, these conditions come from the fact that you have. You had to have some invariant inner product in your phase space, and if you want to choose your inner product in your phase space to be a Lorentz invariant one, it has to have this guy. This has to, yeah, you're right. This has to be the Lorentz metric. Yeah. Exactly. Yeah. Okay. And so now, so now you have 2 problems with this. Two problems. Which, okay, the first problem is that one set of oscillators is that the mu is equal to 0 oscillators have the wrong sign. Okay. And so there are various ways to think about about what having the wrong what this wrong sign corresponds to. I mean, one way to think about it is that if you're doing so you get you get negative inner products in Bargman-Fock. So if you try and write a anyway, yeah. So there are various. You're going to run into a trouble when you're trying to do Bargman-Fock with this negative sign here. And one way of thinking of it is that you managed to create this this kind of standard harmonic oscillator state space, but the for the oscillators in the zero direction, the your inner product is now negative definite, not positive definite. So I mean, the sign can go in it can be moved around various places, but one way it can tell you about it is just that you've got the wrong sign on the. So for these in this time-like basically you have these time-like oscillators, and they're giving you states which have a have kind of they're not unitary in the sense that the inner product is not positive definite, but it's negative definite on these guys. Okay, but that's there's going to be a compensating problem, which in some sense is related, which is to notice that these wave equation doesn't fix the gauge freedom. Yeah. In other words, if a mu of tx a solution, so is a mu. Well, let's take a mu plus, let me call it d mu phi. Oh, if okay. Anyway, so you can figure out what's the condition that if I've got a solution to the wave equation, it turns out if I add something like this to it, then is it going to give me another solution? So anyway, so this is a gauge transformation. So if I do a gauge transformation on it, am I going to get am I just going to move in the space of solutions? And what you find is that the answer is yes, if you if you take a gauge transformation by any function that satisfies this that satisfies the wave equation itself. Okay, and so again, so you have another version of this. You have another version of this problem that we saw in time-like gauge. So you have the problem. So the same problem as in time-like gauge. As in time-like gauge. Gauge is that you have anyway you quantize too big a space. You have these extra gauge degrees of freedom, and they correspond to they correspond to degrees of freedom which just satisfy the wave equation. They're kind of like a massless, they're kind of like a massless Klein-Gordon degree of freedom. So you've got kind of you've got these oscillators that have, you quantize the system that's too big because it's got these oscillators with the wrong sign that are totally messing up your unitarity. But you also realize that, wait a minute, the thing I quantized, I already knew that it was too big because it also had it included these gauge degrees of freedom. And it was the space of solutions. The wave equation I was looking at was too big. It included all these gauge transforms of that weren't physical. So what you want, so you've got kind of one extra degree of freedom here, which you have to kind of get rid of, and you've got one problematic degree of freedom here, the A0. And so there is kind of, what you do is you're kind of a tricky, and so you need, so what you want to do is you want to fix two, the idea is to fix two, you want to put put condition on psi corresponding, I mean, to generator of these gauge transforms, to generator acting on psi is equal to 0, and by I mean generator of these gauge transformations, corresponding to this. And now this gets the anyway. So there's a and that's going to be, well, you end up you find that you can impose the condition. And I guess I'll write it down. Minus the first you think that you want to. So the thing which generates this degree of freedom is basically this Lorentz gauge condition. So it's minus d A0 dt plus a vector psi equal to 0. And again, so it's kind of the anyway. So you want to do this, but it turns out you can't do that. You can't actually. There actually are no states that satisfy that you can show. So, but you have to put plus here. Is that that only the positive energy part. Okay, I'm kind of running out of the time to kind of give you a careful explanation of this whole story. But let me just tell you roughly what happens, and maybe I can say a little bit more next time, but we'll see. And then the idea is that if you impose this condition, so this is called Gutka-Bleuler. And if you impose condition on the states, actually it gets a little bit, anyway, you impose this condition on the states, and then you mod out. I think let me instead of trying to do this too quickly, let me kind of say this a bit better next time. So, but basically, you pose this condition on the states. This condition, what happens is that this condition actually gets rid of those negative. This gets rid of those states with negative norm. The problem is that there are still some states corresponding to 0 norm, right? And so then we have to mod out by states. States of 0 norm, right? And then you get then you get the same physical state space as a Coulomb gauge. Okay, so I think maybe let me say a little bit quickly about this next time before, because I kind of tried to go through this too quickly, and I'm going to miss some. This is a little bit confusing, but the basic idea you can see is that it's as typical as happens when you do gradient quantization. if you do covariant gauge quantization, you end up, you know, with nice covariant formulas and everything, and which are going to behave very nicely when you start to try to talk about the interacting theory. But your problem is that you created a state space which is too big. Again, it's got this gauge freedom you have to get rid of. But the point is that there is a covariant way of procedure you can go through which will cut you down to the physical states. And it has this kind of weird property that it has to kind of be done in two pieces. You impose this condition that gets rid of the negative norm states, and then another condition and then you mod out, and then you've got all these extra states with zero norm floating around in there, and you say, okay, well, I'm just going to ignore those, and then you show that you've got the same thing in Coulomb gauge. So it's a bit of work to show how this works, and I may try to say a bit more about it next time. But this is called the Gupta-Bloiler story. And the maybe just then so this was kind of the state of the art in the especially in 50s and 60s when people are doing quantum field theory. This is kind of how you were really supposed to think about what you're doing when you're quantizing an electromagnetic field and coupling it to quantized charged fields. And one problem with this is that this also has a similar problem that it doesn't behave nicely when you go to the non-abelian case. Because again, when you go to the non-abelian case, what happens is that this anyway, one way of saying it is that this guy, y is equal to 0, this becomes a covariant derivative squared kind of term. It becomes 0, and it's no longer a nice linear equation. So the understanding that you had of what your problem being caused by these extra gauge degrees of freedom, which were just kind of a free field of just kind of a free mass zero Klein-Gordon field, which was giving you states you had to get rid of. Here, all of a sudden, this becomes a nonlinear. Anyway, it becomes a nonlinear field equation. I'm not saying this right, also. Anyway, so but you can't kind of, or maybe you can't again kind of nicely break this guy up into positive and negative energy solutions in any kind of way to do because of these nonlinearities, and so the this Gupta-Bloiler thing doesn't work for Gupta-Bloiler thing doesn't work for Yang-Mills theory. So the story about Yang-Mills theory. So the modern story. Let me just kind of end with this, which I don't really have time to go into at all. Modern story is to what I'll call BRST. P is to introduce these new fermionic variables. Called ghosts. And then you have a new condition, and again you're doing something. So and these ghosts actually kind of correspond to these fermionic variables with these with these kind of wrong sign commutation relations, the kind of thing that you get from the these Clifford algebra relations with a wrong sign, and these guys also. Anyway, so that you then quantize the things that we were talking about here. You also quantize these ghosts, and then you put a you have an operator and I have to call it Q, you can create a new operator on this state space that squares to 0. And what you do is you take your physical state space to be Q psi equals 0, and then you mod out by the things that are equal to. So you look at things that Q acting on here is 0, and then you mod out by the subspace of things that they're equal to Q. They're equal to Q of something. Anyway, this is called BRST cohomology, and there's a long story about this. So I don't. I'm sorry for kind of subjecting you to getting you kind of deep in the into the weeds of gauge symmetry. It's I think it's kind of a fascinating topic, and it's something where there's a lot of interesting mathematics, and the standard physical story does, it's still a little bit up in the air. People, when you actually try and do these things and really understand exactly what they're saying, you get into all sorts of interesting mathematical problems and arguably even physical problems. So it's kind of an area of where even in the simple case of the theory of photons, if you try and do what you're told to do in these theories, you end up with quite an intricate structures just trying to get rid of this gauge symmetry and try to deal with it. And so I wanted to kind of give you a little bit of a flavor of it. I mean, so one good argument, about all this would be today, well, just you should stop paying attention after I left Coulomb gauge, that you really should just stick to the physical degrees of freedom and quantizing those. That if you start quantizing a bigger number of degrees of freedom and then have to get rid of them, you're going to have all sorts of interesting problems to deal with. But the fundamental issue that people face is that if you want to talk about interacting field theories, or you want to talk about Yang-Mills theory, you get forced into dealing with these things because in some sense, because you don't actually know how to in an interacting field theory or in Yang-Mills theory, you don't actually know how to kind of just write down just the physical degrees of freedom, or to the extent that you can kind of write down equations and say these are the equations on the phase space and give you which determine the physical degrees of freedom. You end up with a phase space which is not a linear space. It's some very nonlinear object, and you have no idea how to quantize it. So the what works for us for the Coulomb gauge, which is just explicitly getting a linear space of physical degrees of freedom and quantizing it, that actually doesn't work for Yang-Mills theory or for interacting field theories. So all sorts of other complexities happen. Anyway, I think I should stop there. And this was kind of meant more for just kind of give you some kind of flavor of why the subject is complicated. And I think you find if you look at a kind of field theory textbook, you should see the point at which you start to get into this stuff, and it starts to get very tricky. So any questions about any of this stuff? Okay, well, yeah, so anyway, if not, and again, apologies for the confusion here. I mean, it is, I think this is one chapter of the book. I think I wrote, it's fairly clear. So if you do want to get into the weeds of how this works, you should be able to follow it there. I think what we're going to do, what I mainly want to do next time, I may see if I want to say a little bit more about this, but if not, we'll get on to onto the next story, which is kind of here quantizing solutions of the Maxwell's equations. But next, we want to kind of quantize solutions of the Dirac equation. So if we have, elementary spin 1/2 particles, relativistically, they're solution. They're the things which are solutions to this Dirac equation, and I want to take a couple lectures next week and try to kind of go through the basics of how to quantize solutions to the Dirac equation. And again, it's just this is just going to be free fields. This is just going to give you non-interacting fundamental spin 1/2 particles, massive or massless, which don't interact, but it's still there's anyway, it's kind of a beautiful story. The Dirac equation has all these kind of nice features. Okay. Anything else now?
Yeah, real quick. So I guess this Q is somehow analogous to like an exterior derivative type thing.
So I see. Yeah. So it's kind of a coma. Yeah. So it's kind of a cohomological story. So part of what's going on here is what. Yeah. So maybe just to say something very abstract, maybe relevant, is that that if you learn about differential forms and this D operator, that one way of thinking about what the D operator does, if you have a function and you say that I apply this D operator to it and I get 0, well, that's really just saying that so D of a function is a one form, and its components are all the different derivatives. So saying that D of something is 0 is just the condition that the function be constant. Okay. Yeah. So what's happening in the whole story of de Rham theory and de Rham cohomology is that you're in some sense thinking about the fact that if you've got a manifold, an interesting space, locally, you can ask about this condition. Can I you can look at this condition that D of things are 0, and that's saying that I'm looking at the constants. Okay. Now if you've got some compact manifold and you ask, globally, what are the things that are constants? Well, there's nothing very interesting. It's just the constant functions. But if you ask, okay, what are the things that are locally constant? That equation is true locally, but may not be true globally. And then that actually is the beginning of the story of kind of how do you count, how do you find things that are topologically non-trivial? There are things which in some sense are locally they're locally trivial, but globally they're not. And so the whole story of de Rham cohomology is really about, that if you don't just look at functions, but look at differential forms and take this D operator and don't just look at what it does to functions, look at what it does to all the differential forms, then it has the same kind of story that that you have the de Rham differential. It takes D, takes n forms on your space to n plus 1 forms on your space. Okay. And then it turns out you can actually get topological invariance of your space by looking at things that D. So let's say some alpha that's an element of here that D alpha is equal to 0 modulo alpha is equal to D eta. So if you so this this is an operator whose square is 0. Okay. So you look at things that are called so-called closed forms but modulo so-called exact forms that you divide out things that are in here that are D of something else, and this is what's called de Rham cohomology, and it gives you it gives you some finite dimensional spaces, which for compact manifolds it gives you finite dimensional spaces which kind of tell you about non-trivial topology. Okay. Now what's going on here is something similar. So you're not actually doing so anyway. But this is the beginning of kind of a long story in mathematics called homological algebra. That you've got some kind of so-called functor, like the functor of taking invariance, and you have a situation where that's to really understand what this functor of taking invariance is doing. You have to you have to construct something that's called a derived functor, and you get these higher dimensional cohomology groups here. So here each zero of them is just the constant functions. But the point is you can actually have these higher order things, and so the story of BRST cohomology is kind of formally somewhat similar. You throw in extra fermionic degrees of freedom, which, when you multiply themselves by themselves give you 0. They're kind of like the dx's and that you see when you're doing things, but they're different. And you construct a complex, and you construct an operator whose square is 0 that moves you along the complex, and on the kind of 0 degree things, saying that it's 0 is just that's exactly the condition of gauge invariance that you want. But the kind of weird thing about one of the weird things about BRST cohomology is that there's something a bit philosophically wrong about it. You're doing everything a mathematician would tell you to do in order to get these higher order derived functors and how to get these and to study higher order cohomology. But then you're just using it you're using just the first piece of it to construct gauge invariant things. So there's kind of one of the weird aspects of BRST cohomology is that you can get higher order. You can get analogs of your higher order de Rham cohomology, but I mean it's all very formal. These ghost degrees of freedom are not the same thing as differential form degrees of freedom. And but what you're kind of told in standard things about BRST cohomology as well, don't pay attention to if there's higher cohomology, don't pay attention to it, or try to set things up so that it's not there. So you're bringing into this whole apparatus in which anyway, which looks like you're doing homologic algebra, and then you're not actually using most of it. But the part of the reasoning is that if you do this, you end up with a calculational method which actually works nicely. It kind of reproduces the group de Bloyer thing to first order, and it also is nicely Lorentz invariant and allows you to kind of, these ghost degrees of freedom kind of are nice Lorentz invariant gadgets, and you end up with a nice kind of Lorentz invariant way of talking about what you're doing. But you've constructed this kind of whole cohomology theory, and then you've only kind of used the 0 order piece of it. That's kind of what happened. But it's a long story. I don't know if that helps.
Well, just guessing something. What is Q minus D?
What is Q? What?
So are Q and D something similar? Like, what is Q minus D?
Q and D. Well, so D. This is just something in the theory of differential forms. Okay. And, yeah. So this is something like this. This is just something in the theory of differential forms. Okay. And, yeah. So this is something like anyway. So
I mean, phi also can be written as a differential form. So
no. But yeah. This yes. So here, I mean, this is this BRS. So this is what I would call this BRST cohomology. So this is not the same thing as de Rham cohomology. So here.
Yeah, but so it's what's the difference? Like Q minus D as well.
Well, okay. So here this is acting on differential forms. So this is acting on functions. So this is functions on M. So you've got functions on M. D and then you've got some kind of dx1 wedge, dx2 wedge, dxn. So and you've got some kind of indices. So anyway, so these are functions on a space, and with multiplied by these kind of by these degrees of freedom, which are kind of. I mean, anyway, they have this property that if you take products, they behave in a kind of a fermionic-like way. But that's not really. I mean, this is a very specific and well-defined space. I mean, what I'm saying here, this space, this is just a vector in your space in your Hilbert space that you created somehow. So I haven't actually told you what the states are. Okay. So this is a what you should think of really is that, remember that when I talked about this today, when I was talking about the quantizing the photon, and I was talking about creating these much too big unphysical state spaces that had physical photons in them, but also had these gauge degrees of freedom. You should think about these guys as those kinds of things, but also tensored together, and that corresponds to this. And then, but also there's this kind of thing. So you're also going to tensor together these anti-commuting degrees of freedom, these ghost degrees of freedom. So you're going to throw in some new fermionic variables with the wrong sign norms, and they're going to and then you're going to create this really. I mean, what you're doing is you're taking a problem where you had too many degrees of freedom, and instead of just putting a one condition to cut out those degrees of freedom, you're saying, aha, I'm going to, which would be the analog of just saying that I want d of this to be 0, that's locally constant. You're saying I'm going to throw in all sorts of extra fermionic ghost degrees of freedom and make a whole complex, and then I'm going to take the cohomology of that complex. So you're going kind of way up in terms of, you're dealing with the problem of trying to get rid of a degree of freedom, the kind of thing I was talking about, by adding yet more degrees of freedom, and then doing this. So it's a very it's not at all an intuitive thing to do, and it's not it's kind of it's vaguely analogous to what you do in Coulomb cohomology, but it's actually, I mean, these are, yeah, I mean, I haven't really told you, I haven't at all told you what these states are, but they're kind of they're states in this theory of this kind of too big theory of photons with too many degrees of freedom, tensored with even more ghost degrees of freedom, and then so you created this big thing, but the big thing you created is all nice and Lorentz invariant, and then this guy is a nice Lorentz invariant operator, and so then you cut this big mess down to exactly what you want in a Lorentz invariant way. That's the idea, but I haven't at all told you how to do it. It's a long story. I was actually just looking at, if you really want to know about this, there's a I can read it. So there's a quantization of gauge system. So this is the one book I know where they actually work all this out in detail. So I'm afraid. I mean, if you really want to know exactly what's going on here, there's but be prepared. It's several hundred pages. So I don't. Okay.
Yeah, I don't know. I guess this is kind of one last question. Is there any intuitive reason why you wouldn't use the higher order? I don't even know, groups in this chain complex.
Well, it's higher order BRST cohomology. Well, it's very unclear what its physical significance is. I mean, the 0th order cohomology is the invariance. So that you understand. You understand. I want to pick out of this big, huge state space, I want to pick out the gauge invariant piece of it. That we know. The problem is the higher order stuff, it's, from a mathematician's point of view, it's a derived functor of the functor of taking, invariance, of taking gauge invariance on this. In some sense, it's an example of what you would call kind of higher dimensional Lie algebra cohomology. It's it's a well-defined mathematical object. There's a lot known about how these objects how to calculate some of these objects and what they will tell you about the algebraic behavior of exotic kinds, but there's not there's no in general there's no known physical significance to these things. It may be that there may be some cases where you actually can assign where there is some understood physical significance. I'm not quite sure. And maybe that's the thing. Another thing to say is that if you're trying to understand, well, better not. Anyway, it's a complicated business. At first, I long ago when I started looking at this, started thinking, oh, there must be some kind of simple, straightforward mathematical formalism that you can understand abstractly what this guy is. And I think, over the years, I've kind of come to understand what's going on, but there isn't a simple story to tell. But unfortunately, the story you would like to tell is that we're just trying to find the gauge invariant piece of something. That's the story you would like to be true, but the way gauge symmetries work, a lot of tricky things are happening. Anything else? Okay, well, that's, I guess, that for today, and I'll be around for a while, so do come back and if you want to talk some more.
Thank you. Thank you.